Using Kepler's laws of planetary motion, determine the period of a satellite orbiting 10% the distance between the Earth and the Moon if the Moon's orbital period is 27.4 days. Well, if we look back to the last section, we can see from Kepler's laws of motion that the square of the ratio of the times, the periods, is equal to the cube of the ratio of the orbital distances. So from that, we're looking at the Moon, which we can call T1. So the orbital period of the Moon is 27.4 days. We're looking for the orbital period of a satellite, which we'll call T2. If the distance from the Moon is S1 and the satellite is a tenth the distance to the Moon, 10%. What this allows us to do is not have to specifically worry about the numerical value of the distance to the Moon. 1 over 0.1, 1 over 1/10 is 10. So now all we have is 27.4 over T2 squared. Well, we can simplify and solve. So 27.4 squared is going to give us 751 approximately. Is equal to T2 squared times 1,000, 10 to the third. That means that T2 squared is approximately 0.751. And if we take the square root of that, we have an orbital period of about 0.867 days. One of the nice things about using Kepler's third law when we calculate is that it is unit neutral. In other words, whatever unit you put in, you'll get the same unit out. You can use days and you can use fractions of the orbital distances, whatever you need to use. It's fine. And again, this is simply a review of Kepler's laws of planetary motion and Newton's law of universal gravity. So Norma Jean has a mass of 55 kilograms and Billy has a mass of 70 kilograms. What is the force of attraction based on gravity alone? Well, F is equal to big G m1 m2 over r squared. G is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. 55, make my parentheses rather large, 70. All right, now, what we don't know is we don't know how close they are. So if we assume that they are 1 meter apart, they aren't socially distanced, that makes our calculation a little bit easier because we can square 1 without having to do too much effort. So that gives us about 2.57 times 10 to the minus fifth newtons. So if we're only looking at the force of gravity between these two individuals at about an arm's length, a little less than that away, we're looking at 100 thousandths of a newton roughly. Now let's talk about the idea of work. Well, work is typically something we think of as a force applied through a distance. F dot D, F dot R, whatever. That can be thought of as FD cosine theta. All right, this is the force in the direction of motion or along the direction of motion. If you were to plot work as a function of force, you're going to have a straight line. And that straight line is going to be W over F, which is your displacement, your distance. Not displacement, displacement. So if we talk about how much work is done on mowing the lawn by a person when they exert a constant force of 75 newtons at an angle of 35 degrees below the horizontal over 25 meters. Okay, for below the horizontal would be this, which is the same angle as this because we're having a nice horizontal ground, which is not anything many of us have ever mowed much. F is equal to, excuse me, work is equal to FD cosine theta. So they're doing 75 newtons over 25 meters at an angle of 35 degrees. Which gives us about 1,536 newtons. Not newtons, excuse me, Newton meters. Now this unit, Newton meter, has a special name, and we call it a joule. The symbol is J. Sometimes I will write it as a script J. So convert the work from joules to kilocalories and compare that to an intake of about 2,400 calories per day. Well, so if we know that this work, which was about 1536 joules, we have an equivalence. 1 kilocalorie, whoops, 1 kilocalorie is approximately equal to 4184 joules. So all we need to do is divide that. So we have about just slightly more than a third of a kilocalorie. Now, a kilocalorie is what we call a food calorie. So to work off a nice big grease burger, it's going to take a bit more than just pushing that mower for 25 meters over level ground.